Today we're going to go over geometric random variables. Our next example of a discrete random variable is called the geometric random variable. For a binomial random variable, the number of trials is fixed beforehand. By way of comparison, there are situations in which the goal is to obtain one success. In this case, random variable x can be defined as the number of trials needed to obtain the first success. A random variable that satisfies the above description is called geometric, and the distribution produced by this random variable is called a geometric distribution. The possible values of a geometric random variable are 1, 2, 3, that is, an infinite set, because it is theoretically possible to proceed infinitely without ever obtaining a success. The following situations are examples of geometric settings. 1, if you flip a coin until you get a head. You roll a die until you get a 3. And in basketball, attempt a 3-point shot until you make a basket. These situations involve counting the number of trials until an event of interest happens. A random variable x is geometric provided that the following conditions are met. So our first condition is each observation falls into one of just 2 categories. Which for convenience we call success or failure. Two, the probability of success, call it P, is the same for each observation. The observations are all independent. The variable of interest is the number of trials required to obtain the first success. Let's look at this example. Roll a die until you get a 3. X equals the number of trials until a 3 occurs. First, let's verify the geometric conditions. 1, 2 outcomes. Success is getting a 3. And failure is not getting a 3. Two, the probability of a success is 1/6 for all trials. 3, rolling a die is an independent event. 4, roll a die until the first 3 is obtained. 'Let's calculate the geometric probabilities using the above example. Oops. So we're going to calculate x equals 1. So this is the probability that x equals 1, which is just 1/6. So on my first roll, I get a 3, and that would be 0.167. Probability of x equals 2 is the probability that on my second roll, I get a 3. Would mean on the first roll I don't, so that would be 5/6, times on my second roll that I do, which would be 1/6, which would be 5/36, which equals 0.14. On my third roll, the probability would be x equals 3. First roll, it would be 5/6. Second roll would be 5/6. My third roll, it would be 1/6. That would be 25 over 216, which equals 0.116. And if you look at this, this can also be written as 5/6 squared times 1/6. Okay. Now with this, if I look at this here, you can sort of see a formula for this. This one right here, my formula, if I look at this, would be q to the n minus 1 times p, my probability. Now, if I want to go ahead and use my calculator to find these rather than writing them out, because you could go on forever and ever and see what the probabilities are, and you notice that it's getting smaller and smaller. So you would use GeoMet PDF P, X, and this is for on the nth trial. And then GeoMet CDF would be on or before the nth trial. And for both of these, you need to know that to find your mean, when this is on your formula sheet, it would be 1 over p, which is also known as your expected value. And to find your standard deviation, which is also on the formula sheet, it would be the square root of q over p squared. My rule for calculating geometric probabilities: if x has a geometric distribution with probability p of successes and q equals 1 minus p of failure on each observation, the possible values of x are 1, 2, 3, all the way to infinity. If n is any one of these values, then the probability that the first success occurs on the nth trial is p of x equals n equals 1 minus p to the n minus 1 times p. So you could go on forever and ever and do this, and you do have to show that work. So instead of showing, like we did in the previous example, writing it out each time, you would use your exponents. So 5 6 squared times 1 6. And I notice 1 or 2 plus this exponent of 1 here equals 3, which is our third rule. The strange thing about a probability distribution table for a geometric random variable is that it never ends. That is, the number of table entries are infinite. And if you notice, each one of my values, as I pointed out in the previous example, decreases. They get smaller. So as my table goes on, these values are decreasing. If you draw the probability distribution histogram for the geometric random variable, the histogram will always be skewed right with a peak at the leftmost value. So this is something that you should know. Here's one last formula that you might find useful. You could also use the geometric CDF and its complements. So the probability that it takes more than n trials to find the first success, so this would be n trials to find the first success, is 1 minus p to the n. You could just do 1 minus geomet CDF when you're using your calculator. In my mind, it's often easier to think through the problem for a geometric random variable than rely on formulas. So I often rely on thinking I'm getting it on the third one. So the first two would be 5 6 and 5 6. The third one would be 1 6. So I like to think it out better than actually going through and relying on the formulas that I have here and here. If you want to actually graph this, so it's often easier to graph these. So say I wanted it for like 10 trials. In list 1, you would list 1, 2, 3, 4, and you keep going down the list all the way to 10. In list 2, you would put what you do on your home screen for your calculator. So this in parentheses you would do on your home screen, geomet PDF 164, and you would press the store key, STO, and that store key is right above the on button, and you would store that to list 2. And you do this on the home screen, and it will be automatically stored to list 2. And when you want to see this in your window, for your window, you would just go from -1 to 11 for your x values, with a value of 1 if you went from 1 to 10, if you wanted to see 10 trials. And then for your y values, you go from -0.5 to 0.2, and you go by 0.1. And you like to see a little bit of negative, and why I did 0.2 is my first one was at 0.167. So that's pretty close to 0.2. So that's where my max would be. And then I decreased by 0.1.